Hello everybody, in this video we will talk about the Bode plot, which is a way of representing frequency response characteristics of a dynamical system. Okay, before starting with the Bode plot, let's talk about what's a frequency response from a very simplified perspective. Okay, so let's draw a system, okay, like this. Let's assume that we have a system. That's great, okay, which has an input and output. Okay, so let's call it G of S. Okay, we have U of t and we have Y of t, and let's assume that this input-output system is stable, or somehow it's a part of a bigger system. It is stabilized with external inputs and outputs. Okay, and this is an input and this output, and we can technically analyze the behavior, and we make an experiment such that let's assume that U of t is a sine function. Okay, sine, okay, sorry for that. Okay, U of t is equal to sine omega t. Okay, so if you remember from your signals and systems or differential equation or circuit courses, okay, you should know that under the assumption that the system is stable, Y of t at steady state conditions, it means that when t is going to infinity, okay, when t is large, will be approximately equal to a or m times sine omega t plus phi. Okay, so it means that sinusoid in, sinusoid out. So we observe the same frequency at the output. Okay, it's as a sinusoidal signal, but the main difference is there's a magnitude amplification, or it can be technically magnitude degrees, and there's a phase shift. It can be a lag or lead at the output. Okay, so if we draw it, okay, so let's call it, if this is our original sine wave, okay, our output could look like this. Okay, so let's call it this. So it can have a shift. Okay, so let's call it like this. Okay, so so it can be something like this. Okay, so there's a like phase difference and there's an amplitude difference, but of course the frequency should be the same. Of course, this is true for linear time invariant systems. Okay, that's good. So this is the basic idea. And as you can see, there's a two specific parts that's really critical here. Okay, one is the magnitude part. Okay, there's a change in the magnitude, and the second one is the phase shift. And if we make this experiment for different frequencies, for a wide range of frequencies, from, for example, very low to very high frequencies, we technically obtain the frequency response function of the system. And one way to visualize this frequency response function is the Bode plot. Okay, so how we can compute m and phi if we know G of S, and let's assume that I really don't want to do the experiment because we really have a process. Okay, so if you don't know G of S, you can do it in an experimental framework, and this is what we do in system identification techniques. But if you know G of S, you technically don't need to do the experiments. Okay, so if you again remember your differential equations or signals and systems courses, you should know that, okay, m, which is the magnitude amplification, is the magnitude of G times J omega, and phi, which is the phase shift, is equal to the angle or the phase of the complex quantity G of J omega. Okay, so what we do is we have G of S and we replace S with J omega, and omega is the input frequency. And this complex number, we know that it has two real and complex part. It has a magnitude and it has a phase. Characterize the magnitude and phase shift of the output. As you can see, even a very complicated looking thing can be very simple if you technically use the right tools from linear system theory and signals and system theory. Okay, I will not go into the derivations of these details, but if you want to look at the derivations, you can look at my lecture notes. I will have more deeper detailed derivations and explanations for these specific ideas. Okay, so the idea is how we can visualize or characterize this magnitude and phase function. Okay, in the Bode plot, we have a magnitude plot and phase plot. In both cases, we have x-axis, okay, which is frequency. Okay, that's right. But okay, so what we can do is we can use a linear frequency scale, and it's technically not a good idea for dynamical systems. Okay, so it's good, it's okay, but you cannot capture important details, and high pass and low pass filters can look very different if you look at from the perspective of a linear frequency scale. Instead, what we do is we use a logarithmic scale for the frequency. We use the original units, hertz or radian second, but we label the frequencies in terms of logarithmic scale. Okay, you will better understand when I start examples on the Bode plot. But magnitude is a little bit more different. We use a specific logarithmic scale. Instead of just taking the logarithm, we use the units called decibels. Okay, what is decibel units? Okay, m dB, okay, which is technically the m in decibel units, it's simply equal to 20 times log m, where m is simply equal to the linear or magnitude of the g of j omega. Okay, so how we compute the dB scale magnitude is very simple. You first compute m, g of j omega magnitude. So you compute this complex quantity, you take its magnitude. Okay, that's nice. And then you take its logarithm, multiply with 20. It's the magnitude in dB scale. And what we do is we simply plot the technically magnitude plot, which can look like this for a low pass filter. And you can technically draw the phase plot, which can look like for like this for a typical low pass filter. Okay, remember we utilize a logarithmic scale at the frequency. Okay, phases in linear scale. We generally prefer degrees in the phase plot instead of radians. Okay, frequency can be in hertz or radian per second. It's more like a preference. Okay, and magnitude we use decibel units, which is a specific magnitude scale. Okay, now I will technically show you some Bode plots of the simpler forms, and we will try to learn how we can draw Bode plot by hand using asymptotic approximation techniques. Let's start with an empty Bode plot. So, as I told you before, frequency axis it's here, a logarithmic spaced like this. Okay, phase in degrees or radians, linear scale, Bode plot. This is a decade, the most fundamental unit in the frequency axis, and this is 20 decibels, which is the most important interval in the magnitude scale. And we will try to relate the Bode plots in terms of decades and decibels, and we will try to compare them and talk about some, for example, design criteria based on like decibels and decades. Okay, so let's start with the basics and try to find the Bode plots of S and 1 over S. Okay, let's start with S. G of j omega is equal to j omega. If you look at the logarithmic magnitude, we can see that it's equal to 20 log 10 omega. It's very simple. And if you look at the phase, g of j omega, we can see that it's simply equal to phase of j, which is 90 degrees. Okay, so let's start with the phase. As you can see, it's super easy. It's just 90 degrees for all possible omegas. Okay. So it's just simply horizontal line. If you look at the magnitude, it says logarithm, but since frequency is also in logarithmic scale, so this is, let's say, log omega. Let's consider as a different variable. It's also a line in the magnitude axis, right? It's a simple line. So for omega is equal to 1, n is equal to 0. It's easy to see that. For omega is equal to 10, n is equal to 20 times 1 decibels. So it's 20, so it is 0, it's 20. If I go to 100, we will see that it will be 40. If I go back, 0.1 radian per second, it is minus 20 and minus 40. As you can see, the magnitude plot of S is a line which is an inclination of 20 dB per decade. Okay, it's very simple. Okay, let's go back to 1 over S and try to find its phase and magnitude. Phase is very easy. Okay, so what's the difference in S and 1 over S? It's just phases shifted in terms of we put a minus. So it's easy to see that the phase of this is S, this 1 over S is it's 90 degrees. Okay, we just shift the phase. So what about the magnitude? Okay, so if we compare them in linear scale, magnitude of one of them is omega, magnitude of the other one is 1 over omega. So if we take the log, what happens is log of 1 over omega is equal to minus log of omega. So technically, we just reflect the Bode plot of S with respect to 0 dB line to obtain 1 over S. Okay, it looks like this. For this reason, the second one, 1 over S, has an inclination of minus 20 dB per decade. Okay, so it's here. If you look at the result, as you can see, it's true. So these are the most fundamental and basic functions that we can draw the Bode plots. But you will see that these lines are kind of good way of approximating even more complex Bode plots. And we will see how to approximate first order and second order transfer functions using asymptotic line approximations. Okay, so let's start with a simple transfer function s plus 1. It's not a transfer function, it's just kind of an identity. So, and this is the Bode plot. Okay, so before going to an analytic approximation, if I want to approximate this with lines, what I do is, I think at low frequencies, it's a very good line, right? So it goes like this. At high frequencies, we have a line also like this. So what I do is, let's clean unwanted areas. Okay. So if I clean that, so let's, okay. So maybe this is a good approximation, right? Okay, is it? I think it's true. But we will see that. Okay, so for the face, it can be something like this. Something like this. But for this, maybe I can put a straight line. It can be a good approximation. Let's see that it's correct. As you can see, yes, my like graphical approximation is a very good approximation for s plus 1, and it is the way that you need to draw the Bode plot. Okay, so if you do that, let's look at the magnitude. This is a straight line, just flat. At high frequencies, it's a line, but it has a trend, and its trend is 20 dB per decade because it's a first order argument. For the phase, this is my corner frequency, 1 radian per second. So you have a line that is centered around 45 degrees and your corner frequency, which has a 45 degrees per decade trend. And high frequencies, it's a straight line, which has a phase of 90 degrees. At low frequencies, which has a phase of 0 degrees. Okay, as you can see, a graphical approximation is a very good approximation. But the idea is, how we can guess this graphical approximation if we don't have the actual Bode plot? Okay, let's try to capture that. So let's clean everything that we don't want and try to find the same approximation using some analytical tools. At least some basics. Okay, good. So s plus 1. So what we should do, first start with the magnitude, and dB is equal to 20 log 10 magnitude of j omega plus 1. Okay, this is equal to 20 log 10 square root of omega square plus 1. I know that because it's logarithmic scale, I can write it in this form, log 10 omega square plus 1. Okay, so it's kind of hard to capture this, but at low frequencies, let's assume that omega is close to 0, and we don't know how close it is. This is approximately equal to 10 log 10, 1, and it is equal to 0. Okay, so we can analytically find that this is actually a 0 dB line. Okay, at high frequencies, omega very greater than 1, and 1 is the corner frequency. M is approximately equal to 10 log 10 omega square. Okay, because 1 is negligible, it goes like it's approximately equal to 10 log 10 omega. And I already know this. This is the same function that I obtained with S. So at high frequencies, it approximately looks like S in the magnitude scale. So what is this? If omega is equal to 1, this is 20. Now, this is 0. It is here. If omega is equal to 10, it is 20, 40 like this, and as you can see, it has a 20 dB per decade. Okay, so for the magnitude, we don't try to derive a relation for medium frequencies because this intersection of these two lines, this is low, this is high, captures the graphics pretty nicely. And if you look at this difference, I will tell you later, it is indeed only 3 dB. Okay, it's very small in dB scale. Okay, so let's look at the phase. Let's try to do the same thing with the phase. Okay, let's clean markings. So phase of g of j omega is equal to phase of j omega plus 1. Okay, which is actually equal to simply a tan omega. Okay, because omega is positive, 1 is negative, we can simply use the a tan formula here. Okay, so how we can approximate this? So in this case, we do low, high, and medium. At low frequencies, what happens is g of j omega, let's say phase. Let's use simple thing. Okay. Phase is approximately equal to the phase of 1, which is equal to 0, right? I think it's true. So at high frequencies, this is low. At high frequencies, phase is approximately dominated by the omega, so it is j omega, which is equal to 90 degrees. So we can capture this and this. Okay, then let's look at the phase. So what is phase for omega is equal to 1, which is equal to phase of j plus 1. We know it is 45 degrees. It's like this. Okay, we know that it's a point. So if you linearize the phase arctangent around 45 degrees and use the logarithmic scales in your derivative, which I will not do in its details, you can technically see that it will have this trend. Okay, so this approximation is a very good approximation. Okay, let's look at the final results. Yes, it's true. Okay, so what we do to approximate, okay, sorry for that. So this is the final approximation. So let's clean everything and try to understand. Okay, so in this case, the corner frequency of the magnitude is 1. 1 radian per second. As you can see, this is 1. It's not coincidence. Okay, so until 1, your magnitude is a straight line with 0 dB. And after 1, it is a now ramp, which has a trend of 20 dB per decade. For the phase, at low frequencies, you have 0 degrees. At high frequencies, 90 degrees. So 0 frequency straight line or 0 phase straight line stops at 1 over 10 radian per second. And 90 degrees phase line starts at 10 radian per second. And between 1 over and 10, you have a straight line which connects this point, and this is a very good approximation for first order systems. Okay, so if you know the basics, drawing Bode plot by hand using these approximations is super duper easy. Okay, now let's look at 1 over s plus 1, and we already derived s plus 1. So should I do everything again? No, because I know that. Let's assume that I know the Bode plot of a g. And I want to find the Bode plot of 1 over g. So what I need to do that. So let's get the magnitude. Magnitude is equal to 20 times log 10 magnitude of 1 over g of j omega. Oh, it's great because it's 1 over. So what I do is minus mg, right? So in order to find the magnitude, I simply reflect or mirror the Bode plot with respect to real dB. So my guess is 1 over s plus 1 will have a Bode plot like this. Okay, so same corner frequencies, but now the trend is minus 20 dB per decade. Okay, it's great. So I really like this. Okay, so let's look at the phase. We will do the same thing, right? Phase of 1 over g of j omega is equal to minus phase of g of j omega. What I do is I will reflect respect to 0. So it will be like this. Now I will go to minus 90 degree and it will be minus 90 degrees. So same corner frequencies as you can see. So 1, 10, 0.1. Only thing is now instead of 45 and 40 like important points, we have minus 45 and minus 90 degrees because technically this is a low pass filter. It should have a lag-like phase response characteristics. Okay, so if you look at the results, you will see that it's correct. Okay, good. And these are the actual versus the approximations. As you can see, for both S plus 1 and 1 over S plus 1, these approximations are pretty good for capturing the actual behavior. Okay, now let's look at a little bit more difficult case where we have a different time constant instead of 1. Okay, so if you remember from your Bode plot lectures from circuit classes, you will see that time constant will shift everything in the frequency domain, frequency axis, but technically the shape of the Bode plot should stay same. Okay, so let's try to derive it very quickly, and let's look at the magnitude first. Mg is equal to, for each omega, 20 log 10, okay, square root of t square omega square plus 1. Okay, this is equal to 10 log 10 t square omega square plus 1, which is very simple, but we only have a t. So what is the function of t? T times omega. In the frequency domain, we are technically scaling the frequency, but everything will be the same. Okay, let's look at low frequency. At low frequencies, magnitude will be approximately equal to 0, everything is the same. At high frequencies, magnitude will be approximately equal to 10 times, not 10, 10, t square omega square. Magnitude is equal to 20 times log 10 t times omega. Okay, so at low frequencies, I know that it will be a 0. I don't know where to stop. I'm just throwing everything. At high frequencies, I will have this function. Okay, so let's plug. Omega is equal to 1. What happens? When omega is equal to 1, which is not important. Okay, sorry for that. So what I will do is different. Let's clean. Okay. When omega is equal to 1 over t, let's see what happens. M is equal to 20 times log 10 t times 1 over t, and it is equal to 0. It's great. When omega is equal to 10 over t, I know that m will be 20 log 10 t times 10 over t, and m will be equal to 20. So 0, as you can see, this is 1 over t, and 10 over t, it will be 20. If I follow this, it will be 40, it will be 60. So it will have the same line, but phase shifted or frequency shifted. Okay. So, and as you know, this is 20 dB per decade. So what I should do is, I should simply clean these frequencies, some of them. Like, oh, okay, that's right. And let's clean everything. Complete this. So the main difference is, the only difference is the corner frequency, and the magnitude is equal to 1 over t. From this perspective, we can see that for any first order transform function in this form, what I need to do is compute the corner frequency, which is equal to 1 over t. Then I have the same Bode plot. I just shift it in the frequency domain based on the value of the t. Okay, so let's look at the phase. If we look at the phase, we will do the same thing. If you do the computations and approximation, you will see that it will start at 0. Okay. It will end at 90. And if you compute the phase at the main corner frequency of the magnitude, you will see that it will have a 45 degrees. If you do this for 10 times t and minus t, this will be your approximation. Okay, so the form of a first order transfer function or first order argument in Bode plot is like this. Okay, this is your magnitude and this is your phase. And here the main frequency that changes everything is 1 over t. In the magnitude plot, only there's a one change at 1 over t. In the frequency scales, the frequency structure changes at 0 over t and 10 over t. Okay, so if you know this structure well, you can blindly draw the Bode plot of any first order form. Okay, now let's solve an example. Okay, this is the result. Bode plots of s plus 1 and 1 over s plus 10. S plus 10 and 1 over s plus 10. Okay, so first of all, g of s is not in ts plus 1 form. So we need to convert it to the structure. So what I need to do is 10 times s. Okay, sorry for that, it's not s. Okay, 10 times 1 over 10 s plus 1. Okay, so let's forget the 10 for now and concentrate on 1 over 10 s plus 1. Okay, what is the corner frequency? 1 over t. So what is t is equal to 1 over 10, and corner frequency VA is equal to 10. So everything will change at 10, right? Okay. So if I look at the details, let's look at the phase. Phase should be like this. So I will do the phase. Okay. And magnitude should look like this. Okay, good. For this is true for 1 over 10 s plus 1. But however, we have a multiplication of 10. In logarithmic scale, what is the function of multiplication? It's simple addition. So what I need to do is, I need to add, but I need to add what? 20 log 10, 10. Okay, which is kind of easy to do that, right? Okay, and what is log 10? It's equal to 1, so it's 20. I need to add 20 to this. So let's do that. Okay, so let's. So, okay. This is now the Bode plot of s plus 10. Okay, good. So let's clean the other one. And you can see a multiplication of a constant doesn't change the phase, which is an expected result. Okay, I can clean everything here. Okay, so what about, and let's change the color to this. Okay, what about 1 over s plus 10? Okay, so what I do, if you remember, so if I have g of s, if I have 1 over g of s, in both magnitude and frequency, I look at 0 dB line and 0 degrees line. I take the mirror of the g to obtain 1 over g. Okay, so if I follow this, I need to have this. I'm just mirroring with respect to that, as you can see. And I need to have something like this for the phase. This should be something like this. If I am doing everything is correct, let's check. It's correct. Everything is fine. Okay, so as you can see, s plus 1 has a trend of 20 dB per decade. 1 over s plus 1 has a trend of minus 20 dB per decade. Okay, the corner frequency is 10 radian per second. Okay, technically, this is the corner frequency. In the phase, I have two major chains. At 1 radian per second, my zero phase straight line becomes a ramp, which starts from 0 to go to 90 at 100 radian per second. After 100 radian per second, my approximation says that my phase is approximately equal to 90 degrees. Okay,